Okay, and welcome and thank you everybody for joining us in person and online for today's C2 Smarter seminar rather. I'm Lizzie, the Research Project Manager at C2 Smarter, which is a US DOT Tier 1 University Transportation Research Center. Today we are joined by NYU Shanghai's Professor Zimin Chen, who will present on advancing sustainable transportation, policy analysis, and operation design for electrified ride sourcing systems. Dr. Chen is an assistant professor at NYU Shanghai and a global network assistant professor at NYU. He was a research fellow at the University of Michigan's Department of Civil and Environmental Engineering, and he received his PhD in transportation engineering from the University of Florida in 2017. His research goal is to identify, develop, and implement emerging technologies to achieve a safer, more efficient, and environmentally friendly transportation system. His research interests include network modeling, discrete optimization, and AI in transportation. And as always, we'll be recording this seminar and uploading it to our YouTube channel. And we encourage everybody to ask questions. If you're joining online, you can do so by pressing the Q&A at the bottom of the Zoom window, and then we'll read out your questions at the end. And with that, I'll hand things over to Dr. Chen to get us started.
Okay, thank you. Good afternoon, everyone. This is Zimin Chen from NYU Shanghai. So I'm currently an assistant professor of engineering and also transportation systems. So today the topic I would like to share with you guys is about the advance in sustainable transportation, policy analysis and operation design for electrified ride sourcing systems. So before today's talk, I would like to briefly introduce some of my research interests. So I'm currently focused on the electric vehicles and also connected and automated vehicles. Mainly it's about their techniques and, for example, take for electric vehicle, for example, the first topic I would like to emphasize is the behavior analysis. So one of my jobs is to analyze the real-world electric vehicle behavior to figure out their patterns and also what are the impact factors that affect their performance or the user's behavior. For example, when and where and how much they're going to charge their vehicles. And then, given those behaviors, actually I have conducted a series of research on the deployment plan of the different types of charging infrastructure, especially the ones we consider it as the emergent ones. For example, the power bank, mobile charging, swapping stations, charging lands, something like that. And also, I'm conducting the several research on the charging schedules of electric vehicle users. Okay, how we can optimize those charging schedules from the perspective of, for example, the electricity companies or the bus company or e-hailing companies. Okay. So the last topic I would like to highlight is the policy evaluation and design. Okay, how we are going to evaluate the existing policies to promote the EV adoption, and also how to design the systems. So actually today's topic is belonged to this domain, but the focus is on the e-hailing platforms or the ride sourcing system. And regarding the connected and autonomous vehicles, I mainly focus on the infrastructure deployment. For example, autonomous vehicle lane, autonomous vehicle zones, and roadside unit deployments, and so on. And the other one is about the operation planning for truck photonic, just for example, and also the modular vehicles, which have been investigated by many researchers such as Professor Zhou Chou. So, and also, yeah, interaction. So, and then I turn to today's topic. So, actually, this is actually a video, okay, to show the words how the electric vehicle market change in different countries. But due to time limit, I only show the electric car markets in 2022. As we can see, actually China is currently the largest market for the electric cars. Okay, but for the other country, for example, United States, Germany, actually most of the countries are currently promoting the electric vehicle adoption. So take China, for example. Okay, actually the Chinese government has conducted
and benefits to people who use electric vehicles, such as the license plate law.
Yeah, that means subsidy and
the license plate policy is basically the license plates.
Yes.
Yeah, right. The options and
yeah, for example, Beijing, Shanghai. Yeah, you're right. You're quite familiar with the politics. Okay, yeah, and so in Chinese government, actually they conducted 2 rounds of costly EV demonstration in 2009 and 2012, providing lots of the subsidy. Okay, and however, it turns out that the EV market share is still below 5% by 2019 and 13% by 2021. So, in contrary, for some special fleet, for example, just another case in China, is Shenzhen. Okay, so currently all the buses in Shenzhen have been fully electrified.
well, that's only the government-owned buses. There's also Zhehuan buses that has diesel buses still.
Oh, really?
Yeah, I think Zhehuan is private. So
Because when I saw the
Shenzhen Washington only has electric fleet, but and also that actually they have a mandate that they're only allowed to operate electric.
okay. But according to the news, okay, we always see the
that's
report
government. That's government owned, not
they're government owned. But the majority of the buses are owned by the government.
most.
Okay, good. So 100% by 2017, and then for the taxes, it's 100% by 2022. I think all the taxes should be owned by the Shenzhen government.
Yes, because the medallion.
Okay. BYD, right? Okay, never mind. So
They take the taxi license without having an electric vehicle.
okay. So actually, this is kind of like a comparison. Okay. So and what's gonna be the next fleet to be electrified? Okay. So we expect the ride-sharing vehicles are destined to be the next special fleet for electrification and hold a great promise. Okay, to reduce the greenhouse gas emission. So here are 2 reasons. Okay, the first one is that the carbon dioxide reduction for electrifying one ride-sharing vehicle is 3 times of the one to contribute to the electrification of one private vehicle. Okay, secondary, the ride-sharing market is usually highly regulated. Okay, so it's pretty easy for the government to adapt the current regulatory policies to promote EV adoption. Okay, so but another fact is that electric vehicles only account for 0.15% of miles traveled by Uber drivers in the US and Canada between 2017 and 2019, and 3% by DD drivers in 2020. Okay, the percentage is pretty low, right? Due to the high electric vehicle purchase cost, lack of access to fast charging, significant opportunity costs, and so on. Okay, so what can governments do to accelerate the ride-sharing electrification? Okay, for example, the direct approach is to ban the conventional vehicles from registration. register. This is what some cities in China, okay, they adopt this. For example, in Foshan, okay, in Shenzhen, okay. Conventional or gasoline vehicle drivers, they are not allowed to register as a new drivers to serve the resourcing platform. Okay. However, it's going to yield the driver shortage in the short term, right? Secondly, offer direct subsidies that is going to require a considerable investment and may not be sustainable in the long run. Okay. So, and how about the third part is about the regulation. So, and then if we consider regulation and what type of regulation that we can decide, okay, and how is their performance? What's their performance? So that's the topic we would like to investigate by the first part of today's talk. So before introducing the detailing the policies, I would like to introduce a little bit about the problem setting. So in our problem, we consider an isotropic resource market with a single platform. Okay, the setting must be pretty simple because we would like to capture, as you will see, we would like to capture the interaction among drivers, customers, platform, and governments. So we have to make sure that the setting should be as simple as possible. So, and then for electric vehicles with sufficient electricity or battery level or SOC, okay, state of charge. So, and they're going to behave the same with the as the one of the gasoline vehicles. First, they're going to search for customer, okay, and then they're going to match to a customer by the system and then pick up the customer, okay, and then deliver the customers to their destinations, and finally they tend to the next step to search another new customers. So they repeat this whole process, okay. But so their cost will consist of three portions. One is pick up the cost, pick up time, delivery time, and the search time. Okay. But for the electric vehicles, without sufficient SOC, okay, so once they deliver some customers to their destination, the vehicle have to search for charger to recharge their battery, right? So for electric vehicle drivers, they have to consider the charging time, okay, as part of their cost. So, and in order to capture or to calculate or capture the charging time, okay, we made several assumptions. For example, the electric vehicles considered in this paper, okay, we assume they are homogeneous with the same battery size, and all of them should behave the same in terms of searching for charging station. But they're going to head to the nearest chargers where the battery can only support their trip to that particular charger. And every time their battery is going to be fully recharged, okay, at that particular chargers. And in terms of the charger, we only consider the public chargers, which are uniformly distributed, and also they only provide exclusive service to resourcing the electric vehicles. And we further assume that the arrival of the charging electric vehicle at the charging station will follow a portion process. Okay, so these are the main assumptions. Though I know that some of the assumptions could be strong. Okay, for example, in reality, now the chargers are not going to be uniformly distributed. Okay, however, as kind of like we as the first attempt to investigate different types of policies, I think it's a good trade-off. And then the charging process at a charger can be described as an MD1 queuing system. Okay, this is how we can calculate the charging time cost, the per trip. So we're going to calculate, it's going to include three parts. Okay, once the travel time to the target charger, okay, the queuing time in the charger, and also the recharging time. Okay. So given this, so actually, yeah, this one is used to capture the charging time. So we proposed an equilibrium model, and this equilibrium model can capture the equilibrium, the steady state of the electric vehicle drivers as well as the conventional drivers' behaviors. Okay, so the first part is the matching and the matching and target. Okay, and the second part, okay, is about the electric vehicle and conventional vehicle adoption rates. Okay, we adopt a logarithm model. Okay, and then we simply calculate their utility cost for example, to adopt the electric vehicles or conventional vehicles to serve the platform. Okay, and then we have the customer demand and the conservation. So this is how the drivers, okay, will behave given the policies, okay, and given the distribution of the chargers, something like that. Okay, everything is given. Okay, we can calculate their waiting time, their charging time, and so on, and also their adoption rates. And then we tend to consider the policy options. So in this study, we consider three types of policies. One, the first policy is annual permit fees. So it means that the government is going to set a target EVMT rate, electrified vehicle might travel rate, okay, for that platform. Okay, for example, up to 2025 for DD, okay, the EVMT rate must be just, for example, 50%. Okay, just set a target. Then a platform is going to be charged with an annual permit fee if it fails to achieve the target. Otherwise, it's going to be exempted. Okay, so this is how we calculate it. Okay, and the second policy is we call differential trip-based fees. So the platform is charged with a higher fee, okay, for one trip completed by the conventional vehicles, okay, but a lower fee for electric vehicles. So by doing that, it will encourage that the platform to decide some policies within the platform to attract more electric vehicle drivers to serve the platform. Okay. So the third policy is the differential, the commission cap. It means that the government sets different commission caps on conventional vehicles and electric vehicles. Okay, just for example, okay, the cap for electric vehicle could be higher. Okay, so it means that the right sourcing platform that can earn more, okay, by operating the electric vehicles to serve their customers. That it's a decision. It's a decision variable. So, and then suppose the policy from the government is given, okay, then the platform, they're going to make some response, okay, to maximize the platform's profit by determining, for example, the charger construction. What's the number of chargers I should deploy, okay, and what's the charging power for each charger, and also electric vehicle adoption, the battery in terms of their battery size, and how about the subsidy rate, and also the commission support, and also the price, how I'm gonna decide the price, okay, for each trip completed by conventional vehicles and electric vehicles. Those are the actions the platform can take to make a response to the government's policy. Okay. So then, in order to evaluate those policies, so we propose different index. Okay. First is what I call the effective. If it leads to a new market equilibrium, okay, with a penetration rate, EVMT rate higher than the target, then the target rate set by the government, then we are gonna call this policy is considered as effective. Okay. And the other one is called cost efficient. It's gonna be measured by the change in social welfare for unit fuel consumption reduction. And this is how we calculate the social welfare. Okay. And then we take the ratio of the social welfare and the fuel consumption reduction. So we can calculate those measures. Okay. So first, we're going to consider the effectiveness. Okay. So these three figures shows the control of EVMT rates under three different policies. So the first one is for the AP, the annual permit fees, and the second one is for the trip-based fees. Okay, and the third one is for the commission capped policy. As we can see, if we adjust the parameters, for example, for AP or TB, we can simply adjust their parameters in those corresponding or included by these policies. Actually, we can achieve pretty high adoption rate. For example, if I would like to achieve the 90% adoption rate, then I just need to set, okay, the R0 to be this part, right? I can do that, okay? It's the same for TB, but not for CC. You see, the maximum adoption rate is only 36%. Okay, so no matter, it means what? It means that the government can achieve a higher market penetration by adopting the commission capped policy. So here's the reason behind that is because, for example, if the government set a lower commission cap on electric vehicles, okay, then for the platform, it means what? It means that if I attract more electric vehicles to serve the platform, then actually the profit I can earn is much lower, okay, than operating the conventional vehicles, because their commission cap is already there, pretty low, much lower than the conventional vehicle, right? However, if we set a higher commission cap for electric vehicles, then the problem is that the drivers, electric vehicle drivers, they're not willing to serve the platform because they're gonna earn less, right? So anyway, so this is the reason. So differential commission cap is only effective for EVMT rates lower than 36%. And also for the cost efficiency, okay, we figure out that the CC policy is the most cost efficient. And because the platform, at optimality, the platform is going to charge fewer commissions on both types of drive. Sure, please go.
Sorry to interrupt. So just to clarify for the previous look at the different policies.
Sure.
In New York City, we have taxi surcharges. I guess there's fixed surcharges as well as there is a cap as well for like the number of ride-hailing vehicles and there's like a policy on cap for that's I guess it's being changed for electric vehicles. So this kind of pertains to that, right? Like these
Yes. Yes.
And it's suggesting that maybe having some kind of effective cap might be more efficient than those other policies of like surcharges.
You mean do you mean the effectiveness or cost efficient?
Social effectiveness.
Oh, okay, then
EMT rates.
it should be this one. If you consider the social welfare, then it's going. Yes, you're right. Okay. In terms of our finding, yes. Okay. CC, I mean the commission cap policy is actually the most cost efficient. Okay, in terms of improving the social welfare. So it's because the platform charges fewer commissions on both type of drivers, so the drivers are gonna be better off. Okay, so and in the meantime, the platform will decrease trip fares to attract more customers. Okay, I mean we figure out this because we solve the problem optimally, and that's the outcome. Okay, so and then customers better off. And for TB, okay, it's the least cost efficient because to avoid the chip-based speed, the platform will deliver fewer customers and make more money per chip. Okay, because the chip-based speed, for the chip-based speed, the company, the platform is going to be charged in terms of each chip, right? So in order to make more profit, then you deliver fewer customers and make more money per chips. Okay, set the chip fare to be higher. Okay, so and as a result, the platform surcharge drivers and customers, and the market will shrink. And then as a return, both drivers and customers worse off. So that's the logic behind this. Okay, we try to expand this phenomenon. Okay, and then we also consider the platform's optimal strategy or platform's response. Okay, in terms of their optimal battery size. Okay, charging power. Okay, and also the number of chargers. As we can see, and okay, I would like to highlight in this numerical example, we consider 3 scenarios. One is the optimistic. It means that given the advance of the vehicle technologies, especially for the batteries, okay, we imagine that the cost for electric vehicles is going to be reduced, okay, by 10%, for example, in the near future. And for the pessimistic, we consider that given that the government, okay, is going to reduce their subsidy, okay, then maybe in the near future, people may have to spend more money to purchase electric vehicles, okay? So we also consider that. So as we can see, no matter under which scenarios, the findings are quite common. For example, small batteries are preferred to avoid high adoption cost. Okay, this is reasonable. Okay, and
not necessarily like, well, small battery kind of basically means that you can drive fewer miles per day. And I think it really depends on who, like, it kind of really depends on what kind of drivers you want your advertising. So,
okay,
like I would not say that this is general, but like for some people it is, but for some other people it is not.
Yeah, because as you may notice that in this paper, actually we assume that the platform can control, okay, the battery size. For example, under what type of battery size, then you're allowed to serve my platform. Okay, so given that, okay, the platform may prefer small batteries. Okay, but as you mentioned, small battery may suppose that the drivers have to recharge their vehicles more frequently, right? So the outcome, I mean, we can deal with that. Okay. The second finding is that we can use fast charging, or the platform are going to adopt the fast charging chargers and gradually expand the charging network to accommodate the charging speed. Okay, so that's how they can combine that. Okay, for example, if the charging power is pretty high and we have lots of chargers available, then small battery is not going to be a problem. Okay. So, okay, this is the end of the first part. Okay, and given that, while considering how to promote EV adoption in the resource market is very important, right? It's also pretty important to consider how we can better serve the current existing electric vehicle drivers in the resource platform. Okay, so we can see, actually this is one figure we draw based on the real world data in Shanghai. Okay, as we can see, these are for the commercial vehicles, and most of the commercial vehicles can be considered as the ride sourcing vehicles. Okay, in Shanghai, as we can see, there are 2 peaks. Okay, these 2 peaks, these are the charging this is the distribution of the starting time of charging sections in the workday in Shanghai. So these two cases means that most of the right-sourcing vehicle drivers, they are willing to charge their vehicles at these two time periods. Okay, so these two periods are actually the off-peak hours for the right-sourcing systems. Okay, you see at road. Okay,
Yeah.
The customer, not many customers at work. Okay, and also the drivers have to take a rest, right? And time, okay, after the peak hour. Okay, so then what's going to happen? For example, if the electric vehicle, the market penetration keep increasing, and most of the vehicles are going to recharge their vehicle at the same time. Okay, it's going to be a burden for the grid network, right? So then the first question is that how we can model this behavior mathematically, okay, about the work schedule of the EV drivers. And then the second problem is that is it possible that we can jointly optimize the charging and also the order dispatching behaviors simultaneously? So that's the third topic. Okay, and so in terms of the second topic, so for example, for electric vehicle drivers, their work schedules consists of three portions, okay, or three components, three parts. Okay, one is to work. Okay, the second one is to take a rest. Okay, and the third one is to recharge their batteries. So if a driver considered to work, okay, she can earn the more money, okay, but she have to spend, for example, spend time, okay, becomes more time, and also spend electricity, okay. And but if a driver chooses to recharge their vehicle, then they can increase their battery size, their battery level, right? And in the meantime, charging behavior can be considered as a type of resting behavior. They can refresh themselves. Okay. So but at a cost of losing the kind of like money which they should have earned if they keep working. Okay, and also spend time. So the driver's payoff is equivalent to the gains minus the losses. Okay, so each driver will decide her work schedule to maximize the payoff, considering both limited charging opportunities and driving behavior. Okay, so how we can model this? Okay, so we actually establish a model based on the time expanded network. Okay, then we can convert the schedule choice into the path choice. Okay, for example, in this network, we have we have 6 types of links. Okay, but the most important is the work links. Okay, rest links, recharging links. Okay. If you visit a particular part of link, for example, the word link, it means that you choose to work at this period. Okay, so because there are 24 hours, so we consider 1 hour as a period. Okay, so this is the origin, this is the destination. So a path from O to D actually corresponds to a work schedule. Okay, for a right-sourcing driver. For example, this driver, particularly this driver, chooses to work at 2 a.m. and then stop at 11 p.m. Okay, but anyway, this is just an example. So, and also if the driver chooses to have this particular charging link, we have to consider there is only limited number of chargers available. Okay, so we are going to impose a capacity on that particular link. Okay, so if the link, this is a kind of like a time constraint. So the flow on that particular link cannot be over the capacity. Okay. And then we also consider, then we can calculate the corresponding SOC dynamics. Okay. For example, when an electric vehicle travels a work length, then it's going to consume electricity, right? But if it visits successfully the traverse a charging length, then it's going to be fully charged. Because here we consider 1 hour as a time period, as one period. So 1 hour is already sufficient for an electric vehicle to be fully recharged by a fast charger. Okay, so the past choice rules is to maximize their profit. Okay, so then first we would like to consider, okay, how to calculate the profit. Profit is equivalent to the difference between the revenue and the cost, right? First, how we can calculate the revenue. So, okay, so this system, actually these four equalities, they together, they can capture the relationship among the elastic customer demand, customers waiting time, driver supply, and the number of occupied cars at each time period. Okay, so given the driver supply, the output of this system is unique. Okay, can be unique, determined. It has been proven. Okay, and then given that the driver's average revenue can be calculated as a function of UT. Okay, this is an intrinsic function. Okay, but anyway, it can be calculated. So and then we turn to the cost. Driver's cost includes the link-based and also the path-based costs. For the link-based costs, for example, the rest time cost, the driving home cost, and so on. Of course, the gas or battery consumption cost. All those costs are link-based. Okay. And for the path-based cost, it's going to be used to reflect the mounting the distributed from long and continuous drive working. So in the literature, we normally consider the past cost as a function of the total working hours for the whole day. Okay, but this is may not be. This is considered as the cumulative work hours. But in our model, we further consider, okay, in addition to the cumulative work hours, we consider the consecutive work hours in the work segment. So this term is actually the vertical cost, the driving vertical cost. I'll show you an example. For example, these are two segments. Okay, the drivers conduct continuous working behaviors. Okay, this is one segment. Okay, and then after working for 4 hours, the driver takes a rest for 2 hours, and then keep working for another 4 hours. Okay, or maybe 3 hours anyway. So given that for this segment, we have a function. I mean, we adopt this function to calculate the vertical cost at this segment. Okay, and after 2 hour rest, definitely the driver is going to be refreshed, right? So no driving vertical anymore until this segment. Okay, so we consider, I mean, if this is the whole day trip, then this is the vertical cost is equivalent to the driving vertical of this segment plus the driving vertical of the other segment. Okay, so it's totally the path-based. Okay, and I'm going to show you another example to emphasize. Actually, involving this type of cost is rather difficult for the solution algorithm design. So as we can see, our formulation is kind of like a general case. Okay. So, and mathematically, it can be formulated as a coordinate programmed formulation. Okay. Solving this problem, actually the outcome will reflect the equilibrium condition. So each driver will choose their the work schedule to maximize their profit. Okay. So, but solving this problem, there are going to be two challenges. First, some functions are path-based cost. Some costs are path-based, as we can see. So we cannot apply link-based method to solve it directly. Okay. Secondly, it involves an implicit function regarding the revenue. Okay. So we cannot directly solve the COMEX program. So how we can deal with that? We adopt the gap function-based method proposed by Law in 2000. And by solving this model, actually, if we can optimize this problem with an objective value equal to 0, then it has been proved that the solution is also the optimal solution to the COMEX program we just present. But for that problem, we have to enumerate all the passes, okay, which is time consuming, okay. And to avoid that, we integrate the method with the column generation scheme, okay. We only generate the chips that is necessary, that we consider necessary, which may yield a a higher profit, okay. So, however, when adopted the column generation scheme, we figure out that the subrouting of the column generation includes non-additive shortest path finding problems. Okay, this is for the gasoline vehicle. This is for the electric vehicles. Okay, both of them are non-additive shortest path finding problem. Non-additive shortest path finding problem. For example, I would like to elaborate a little bit. It's due to this term. Okay, this is the cost. Okay, as I mentioned. So this part is used to calculate the driving fatigue. Okay, it depends not only on the length it contains, but also on their order of appearance. For example, these are two work schedules. Okay, though their total number of working hours are exactly the same. Okay, but the number of working hours in each segment, they are different. So as a result, this function, I mean, the outcome, the calculated driving fatigue would be totally different. Okay, and we figure out that at that moment when we write this paper, no algorithm deals with such a task cost. Okay, so we develop a multi-objective label correcting algorithms, which can find the global optimal paths. Okay. So and then we also propose some techniques, okay, to speed up the solution algorithm. First, we consider the bounds on the number of work lengths, consistent dominance, loop exclusion, and charging time regulation, something like that. So here, this is some numerical example. Okay, given the potential demand, this is given. This is considered as the input. By solving our model, we can show the realized demand as well as the driver supply at each time. Okay, at each time period. And accordingly, we can also calculate the revenue and the number of vehicles in different states. Okay, so generally, resting and recharging happen at off-peak hours with low revenue. You see, this is quite consistent with the data we analyze, right? Meanwhile, a few drivers are observed to rest or recharge at peak hours, okay, to bypass the competition at the charging stations. So if we look at the detailed work schedules for the gasoline vehicles and electric vehicles, we figure out that electric vehicle drivers are willing to work longer than the gasoline vehicle drivers, okay? Because they have to spend time to charge it, to recharge their vehicle. So in order to make more money, they have to work longer compared with the gasoline vehicles. Second, some electric vehicle drivers will choose less profitable paths to bypass the competition for chargers. Okay, if everyone would like to recharge their vehicles during the off-peak hours in the right-sourcing market, then there's going to be congestion in the charging station, right? And then it's a waste of time and also yield a higher opportunity lost. So some of the drivers will choose to bypass this time. And also our model, they capture the queuing delay due to limited charging opportunities. Okay, you see, before charging, you figure out that some drivers actually they will first take a rest. Okay, so the reason is because at that moment all the chargers are fully occupied by the other drivers.
The first point that EV drivers are willing to work longer than EV drivers, do you assume the cost of charging is the same, or like if it's a lot cheaper to charge, does that tend to grow? Does that have impact?
Good point. It could be, okay. But in our case, we actually in our model we also consider the price for the gas, okay, gas consumption, and also the price for the electricity the consumption, okay. But this is the outcome. Yeah. So it means that the electric vehicles already make a trade-off. Okay. And also another reason it could be that in our study, we only consider 1 hour as a time period. Okay. So once if you choose to recharge your vehicle, you have to stay there for 1 hour. Okay. That's gonna be another problem. Okay. It may also affect, I mean, that's maybe one of the reasons we get this result. Okay. Thank you. Any questions? Okay. And we also figure out some nonlinear effect on of the charging capacity in terms of the average charging inconvenience and also the driver's average hourly profit and the platform emission. Okay, we can see, I mean, according to these two figures, it might be good to consider that, hey, for the rest of the platform to deploy only, for example, 80 or 90 chargers. So, and then we can achieve a higher profit, and at the meantime, the drivers can suffer less charging inconvenience. Okay. So this is for to test the speed, the efficiency, the performance of the speed up technique. So given that we only have 10 minutes left, okay. So I'm gonna quickly go through the third part. Okay, is how we can jointly optimize the order dispatching and charging. Okay, of the driver's behavior. So okay, so coordinate the electric vehicles charge and order service activities to increase the revenue of the platform as well as the service level. Okay, it's pretty necessary because as we can see from our model and also the real world data, without any coordination, most of the drivers will choose to charge at the same time, right? And this is gonna yield, for example, crowded and long waiting time at station, and at the meantime, shortage of electric vehicles in rush hours, if lots of people keep waiting in the charging station, right? So this is just to highlight that not many literature has considered the joint optimization of charging and order serving. Okay, so in this paper, we consider the time variant uncertainty of orders and the dynamically the changing workload of charging stations. Okay, and we propose an online SARS SAA algorithm to solve this problem. So the problem setting is pretty simple, but this is a real world problem setting. So some companies they own an electric vehicle fleet, okay, to provide exclusive service for certain transportation hub, for example, the airport, a particular airport. Okay. So for those for these vehicles, for those electric vehicles, okay, some of them may need to be assigned to charge, okay, because of the low SOC. Okay, and once they are fully recharged, they are gonna come back to serve the companies, to serve the customers in the transportation hub. For the other vehicles, okay, some of them may be assigned to serve to fulfill the request of the random demand. Okay, so this is so we have 3 types of vehicles available electric vehicles, out of service electric vehicles, okay, which are charging, okay, are being charged at the station and also on service electric vehicles. So the question is that which electric vehicle should be recharged, okay? And secondly, which electric vehicles should stay on to serve which upcoming orders, okay? So this is actually a centralized charging and dispatching system. So at the beginning of each period, the platform observes passenger demand, okay? And then the number of electric vehicles with different SOC levels, okay? Those are mounted to the system, okay? At each time period, not in the future, okay? The current period. So the charging decision is that, hey, at each time period, which vehicle, electric vehicles, so K means that the level of SOC of that particular vehicles. So XTK means the number of electric vehicles with level K SOC at time period T, okay, should be assigned to charge. And this is the order dispatching decision, okay? How many vehicles, okay? And what type of vehicle should be assigned to serve what type of order, okay? So there are two features. So one is that the vehicles are renewable resources, okay? And because electric vehicle will return to the transportation hub in future times with updated state, no matter it's assigned to be charged or it's assigned, they are assigned to serve customer, they will finally come back, okay, to the become available electric vehicle fleet and to serve the customer again in the near future. Figure 2 is that the random orders with unknown PDF, okay? So an order is satisfied if there is an available electric vehicle with sufficient SOC, okay? Otherwise, it may be lost, okay? So, and then we propose MDP model to model it. So X and Y are the decision variables, and then we have some state space, okay? So A, it means the number of available electric vehicles, okay? B is the out of service vehicles. P is the, this is the on service, and P is the out of service. So, and then we can easily calculate the reward function. And then the problem is to find the optimal policy to maximize the expected sum of the revenue over the whole horizon, okay? It could be, for example, 1 month, 2 months, or even 1 year, okay? So, and the motivation of the algorithm design is that, okay, though we can model the problem as an MDP model, but the problem is that it involves large state space and action space, okay? Applying the solver to solve it cannot yield the optimal solution, okay? And also, many states are actually irrelevant to has nothing to do with the optimal solution, okay? And also, one day is just one sample. So the data we have is consists only only 2 months, okay? 61 days. So it means that we only have 61 sample. So the sample is quite small, okay? So given that, we propose a SAA algorithm. First, we explore a high quality action based on the sample average approximation model, okay? And then we explore and update the value of the expected action for the observed state based on the SASA algorithm. So here, the delta, it means that how many times that the delta times that we are going to look forward, okay? Because we notice the decision I made at the current stage may not have impact on the state, okay, far away, okay? So we only focus the delta future step. And the value of the state action pairs can be calculated by this one. Okay, so and then this is the SAA model. Okay, we just sample. Okay, J set of samples. Okay, and so given those samples, actually this is a deterministic model. We can solve it by commercial solvers. So, and this is the overall algorithm. First, if the state it has never been visited before, then we apply the SAA-based algorithm to solve it. Otherwise, we apply the SASA to update it. Okay, and then we use the history, all the data collected from Tehran company. Okay, it's a company that in Sichuan, and it provides exclusive service to Chengdu Shangniu International Airport. So that's the problem setting. Okay, and we compare our approach with the ADP approximated dynamic program, and also the another heuristic algorithm. Okay, and then this is what the data looks like. Okay, and this is one of some outcome. So this is the revenue, as we can see, compared with the heuristic and also the ADP. Our approach actually improves the average daily revenue by 31% and 14% over 61 test days. Okay, and for this one, this shows the workload rate of chargers for each period under 3 approaches. So we can see, okay, this one, the light blue one, okay, it shows our approach. It can yield an average utilization rate close to 100%. Okay, while the heuristic cause overloads and underloads frequently. Okay, we can see this one. Okay, so and also some simulation results of the SASA SAA and all the one without the sample average, the SAA. Okay, so this is the one with the SAA. This is the one rely only on the SASA algorithm. Okay, you can see the value iterations, the value of each iterations based on the same initial state. Our approach yields much higher value. Okay, this is the first signal. And if we compare the gap with the optimal one, okay, we can figure out that our gap is much smaller than the one that rely on SASA only. And if we compare the state decision pair and the decisions per state, we figure out that ours is much smaller than the SASA. What does it mean? It means that our approach only focuses much fewer state decision pairs, which is very important or closely related to the optimal decision. Okay, we ignore the other useless state decision pairs and also the decisions per state. Okay, so this is one example. Okay, this is the estimated value of the top 300 state decision pairs. The blue one is our approach, and this rectangle one, okay, you can see it's only based on the SASA architecture. Our value is much higher than this one. Okay, so it can expand this one, and also the updated terms. Okay, ours is much higher than the one for the SASA. Okay, this is good. Okay, and that's all for today's presentation. Okay, so all of those findings are actually published online. So if you're interested in the details, you can either raise the question now or you can look at the papers. So yeah. Thank you. So any questions?
Did you have any long-term calculations as sort of electric fields get old, as electric cars get older and their charging time, and the amount of charge lasts amount of time?
Okay, this is about the battery degradation. Okay, yeah, we do have one paper considering that. Okay, one of my PhD students also here, Yan. Okay, we did consider the battery degradation. Okay, but only for the trucks. But for this study, we don't. Okay, because what we consider is the equilibrium state. Okay, as you can see, most of them we consider is either the equilibrium state or the operations level for only 2 months, right? So there it's not a good thing or there's no need to consider the battery degradation. Okay, but you're right. The battery degradation is an important factor to affect the driver's behavior or whether they are gonna adopt electric vehicles. Yeah.
So you talked about the non-additive shortest path problem.
Yeah.
And so you guys came up with a global optimal solution algorithm.
Yeah.
It's like an NPR topic, right? Yeah. So there's applications on that, or applying that to like transit networks, fare prices.
Oh, really?
Yeah, I think Yafen has done some work on that.
Okay.
Local, toy company.
Oh.
Yeah.
Okay. Did they propose some solution algorithm can solve it
They
globally?
ended up investing. They couldn't solve. I think that's so.
Okay. But even for that problem, if the solution algorithm is not that simple as what it looks, I mean, in the slides, yeah. Yeah. So you have to spend a lot of efforts. Yeah. Good question.
So how would you describe the actual response of commercial drivers, especially in their psychological impression to electrical vehicles? And I know that a lot of drivers, they don't like electrical vehicles because in their impression, they're just known to be that they have to take longer rests because they have to charge. So like how closely related, like how similar would you say the results of this study is to compare? How similar is the results of this study to the actual responses of drivers?
So the actual response of the drivers, okay.
How similar is it? How similar would it be? How, like or just make an assumption, like how similar would for study? How similar would they be to drivers? Assume just like how similar.
Actually, in just for example, in Shanghai, okay, I cannot say most, okay. Many electric vehicles actually they are hybrid.
Hybrid or
Hybrid.
like according to what I've heard from bus drivers, they say hybrid is even worse because
Really?
yeah, they're heavy to drive, they're really heavy and they actually burn and the price isn't like much lower, and most of the time they will still have to actually pump in fossil instead of going like near 100% electric. And plus Shanghai taxi I don't think a lot of them allow hybrid vehicles anymore, so they're mostly electric.
Okay, good point. So first, in Shanghai, I believe, I think that I have taken many resourcing service served by provided by the hybrid electric vehicle driver. Okay, because for those vehicles, actually most of those vehicles are rented from some company. Okay, to the driver, they do have the plate license. Okay, and actually not until this year, the beginning of this year, okay, hybrid electric vehicles are not allowed to get the green
Some are. Well, it depends on what kind of hybrid. So if it's
Oh, plug-in,
Yeah,
plug-in, plug-in.
Sure.
What I meant is plug-in the hybrid,
Plug-in,
plug-in, PHEV. Okay,
okay.
yeah, and secondary. So I have personally, I have one experience, okay, to order, to order, to use the resourcing service, from Guangzhou, from my hometown, okay, another city about, maybe 100 miles, okay, and at night, actually, I make the four orders, and finally get the confirmation. And for the first three, actually, the problem is that I'm matched with some electric vehicle drivers, and then the driver contact me. Unfortunately, you have to wait for half hours, okay, because I'm currently recharging my electric vehicle. And the third one, the funny thing is that the driver picked me up and start to drive, and he asked me, hey, during the trip, is it possible for me to recharge my vehicle for half hour? Okay, and then I say no, and then I have to cancel the order. So, and then I made a fourth order and finally get some. So the range anxiety and also the SOC problems need to problem. Okay, as you mentioned, and as you can see. So currently for some resourcing platform, they're gonna assign, for example, for the long trip order, they're not gonna assign those orders to the electric vehicle. Okay.
Yeah. Well, I think the thing is that some drivers, they like long distance orders, but like, they will think that if they bought an electric vehicle, then they wouldn't be able to do it and not be able to earn the money. So I think that might be this encouraging factor. So
Not being able to make money, what do you mean?
like,
Is that-
they can't get these big orders. Like, these are very profitable,
Yeah.
and they want to do it. However, because of the limitations of electrical vehicles, so they might get this and covered from it. So
Okay.
Yeah.
It could be, yeah, good.
So would you say like that, would you say like because of that concern, would a significant amount of drivers not use electrical vehicles?
I think they're gonna make a trade-off
Well,
to be honest,
so,
to balance,
okay,
okay,
alright,
because
so,
the electricity price is much lower than the gas.
yeah, so I would assume, so like, I'm gonna assume that you think that, it's not gonna.
Yeah. So at least in our study, yes, we have to make such an assumption. Okay, but as we figure out that, it turns out that the battery may not be, I mean, should not be that huge if we have sufficient number of chargers and also the charging power is high enough. There's no difference, I mean, between electric vehicle and gasoline vehicle. And particularly, we consider the battery swapping stations. I mean, for some companies such as NIO in China, right? It only takes a couple of minutes to swap their batteries, right? So that's good. That's very good. Okay. Any other questions? If you don't, then thank you for attending today's talk. Thank you very much. Okay.